Alright, this video is an explainer video about a Kahoot quiz that's about stereochemistry and chirality. If you haven't tried the Kahoot quiz, then go down to the link below this video and you can have a go at it. Or if you're an instructor who would like to use this quiz in your own course, then you can go to the same link and include it in your course and then direct students to this video if they want to see worked answers. So the first question on this Kahoot quiz is about these four molecules. In fact, the first several questions are about the same four molecules. The first question asks, which of the following molecules are identical? So what we need to do is manipulate these molecules in such a way that we can rotate them and see whether the atoms will overlap with each other. So if we get, for example, compound D here, and we rotate that molecule around that axis that goes through the molecule like this, rotate around by 180 degrees, then we can make that bromine that's on the right over here, make it spin around to the left. And as it spins around, because it's coming out towards you, as you spin it around, 180 degrees will now be going away from you or behind the page. And so as we spin that around, we'll have a bond that will come now. This atom here will be off to the right, and the bromine that's attached to the carbon next door is now going to be into the page like this. And then we're going to go down to this atom here, and then the bromine that was into the page or behind the page is now going to be coming out towards us. So that's going to be up like that, a wedge bond, and then our final atom is down here, is that final carbon atom. Okay, now if we look at those two molecules, C and now this D that's been spun around, we'll notice that where we've got a up bromine here, we've got a down bromine here, or a bromine going away from us. And where we've got a bromine going away from us here, we've got a bromine coming towards us here. So that manipulation of spinning the molecule has not made it the same molecule. Well, you might have noticed that these two molecules are mirror images of each other. So there's a mirror there. They're mirror images of each other, but when we spin D around, it doesn't overlap, or it's not superimposable with C. And so these are not the same molecule. They're in fact enantiomers, and that will come up in a later question. What about if we do the same thing with B? If we spin that molecule around, now this carbon atom here will go off to the right like that, and this carbon atom here will be an up bromine like so, and then as we go down to this one here, we'll have a up bromine, and then we'll have a down carbon atom like that. Okay, so it's drawn in a slightly different way here, but if we rotate, so what we've done there is rotate the molecule around an axis like this. But if we just tilt the molecule this way a little bit, we can redraw it so that that first pair of carbons is like this with an up bromine, and then a bromine there, and the final carbon atom down that way. And now hopefully when it's drawn like that, hopefully what you can see is that that is the same as A, drawn exactly the same way. So all we've done is rotate the molecule in space, draw it in a different, from a different angle, but it's still the same molecule. And so A and B are the same. So A and B are identical, and therefore the blue triangle is the correct question, the correct answer to this question. Okay, so let's look at question 2. Same four molecules. Which one of these molecules is a meso compound? We already know that A and B are equivalent, so whatever we say for A will be the same for B because they're the same compound. And if we look at A, hopefully we can see that there's a plane going through the middle of this molecule. So let me just sort of draw this as a plane like that. That reflects one half of the molecule onto the other. So if we wanted to, we could draw in our implicit hydrogen there, just to make it really obvious that each one of those carbon atoms is being reflected onto the other one. So this molecule has an internal mirror plane, and that's the definition of a meso compound. A meso compound must have an internal mirror plane that reflects one half of the molecule onto the other, and that makes the molecules achiral. So in other words, the mirror image is superimposable, and we already saw that in question 1 when we looked at A and B and rotated them around. Now, we can't do the same with C or D. If we try to draw a mirror plane, no matter how we rotate this molecule, we can't reflect all of one half of the molecule onto the other half. And so the answer to this question is either the red triangle, A, or the blue diamond, B. They're both correct answers to this question. Question 3 asks which of these molecules are enantiomers? And really we've already answered this when we looked at question 1. We showed that C and D are non-superimposable mirror images, and therefore it's C and D that are enantiomers of each other. So remember the definition of enantiomers is non-superimposable mirror images, and therefore C and D are the enantiomers here. A and B are the same compound. Now if we compare A and C and B and D, we'll find that they're not mirror images, but they're also not the same molecule. They're different three-dimensional arrangements of the atoms, and that'll come up in our next question. So question 4, which of these molecules would be optically active? And optically active is a way of saying that they will rotate plane polarized light. And therefore they will have a non-zero specific rotation. So the specific rotation is a measurement that relates how much they'll rotate plane polarized light given a particular concentration and a particular path length of the cell through which the light is passed through. So to be optically active or have a non-zero specific rotation, the molecule must be chiral. Okay, so must be chiral. And we also must have more than one enantiomer than the other. Okay, so more of one enantiomer than the other. If we have equal amounts of the two enantiomers, one will be rotating the light one way and one will be rotating the light the other way. And so a racemic mixture, 50-50 mixture of the two enantiomers, will overall have a zero rotation of the plane polarized light. So we know that A and B are both achiral molecules. So they can't have a non-zero specific rotation, and we would call them optically inactive. C and D are enantiomers, and individually they'll have a non-zero specific rotation, and therefore each of them will be optically active. And so there's two correct answers. Both the yellow circle C and the green square D are correct answers to this question. Question 5, which of the following molecules are diastereomers? So we already talked about this previously. C and D are enantiomers. A and B are the same compound, but if we compare A with B, and I'll just change my arrow that I use here. Okay, if we compare A with C or B with D, either of these comparisons, we're comparing diastereomers. Because they're different three-dimensional arrangements of the atoms, but they're not mirror images. If we try to draw A as a mirror image of C, we would find we can't draw it so that all the atoms are reflect across to each other. So A and C are mirror images, and B and D are mirror images too. And so both the yellow circle and the green square are correct answers to this question again. Question 6, which of the following statements is true? So A and C have different molecular weight. So we know these molecules all are isomers. They all have the same molecular formula and the same molecular weight. So that can't be true. C and D will have different melting points. So C and D are enantiomers. And in an achiral environment, enantiomers have all the same physical properties. They'll have the same melting point, the same boiling point, the same solubility, the same color, UV spectrum, proton and NMR spectrum, and so on. So C and D will have the same melting point. So the blue diamond is also incorrect. C and D will react at different rates with ethanol. So enantiomers will react the same rate with achiral molecules in achiral environments. So they'll have the same reaction rate with ethanol. So we'll just draw out the formula of ethanol there. So that's also not true. However, if we take one of these enantiomers, for example C, and we react it with butanol, so let's see if we can draw this right. We'll have OH, 1, 2, 3. We've got the R configuration of 2-butanol there. That's a chiral molecule. We're given it as one enantiomer. So that chiral reagent will react at different rates with one mirror image of this compound versus the other. So C will react at a different rate to D with one enantiomer of 2-butanol. So this one is the true statement, and therefore the green square is the correct answer to this question. Same compounds again. How many stereoisomers are there of this molecule, 2,3-dibromobutane? So we said that A and B are equivalent. So they're not stereoisomers, they're the same compound. So that's 1. C is another stereoisomer, 2. And D is a third stereoisomer, 3. So there's 3 stereoisomers that we can find amongst these drawings here. Are there any that we've missed? Well, no. There's only 2 stereogenic centers. So there's 4 maximum possible stereoisomers. However, because one of these stereoisomers is a meso compound, the mirror image of the meso compound is the same compound. So that sort of reduces the number of stereoisomers by 1. So we've only got the meso stereoisomer plus the 2 enantiomeric or 2 chiral stereoisomers. So overall there's 3 possible stereoisomers of 2,3-dibromobutane. And this will always be the case if we have the possibility of a meso compound. It will reduce the number of possible stereoisomers of a molecule that has chiral centers. Okay, moving on to question 8. One stereoisomer is shown for ibuprofen, which is an analgesic that you may have taken yourself for a headache or for inflammation. It's a non-steroidal anti-inflammatory, so it's used a lot and it's readily available in most countries. How many stereoisomers are possible for this compound? So immediately your eye may be drawn to where we've shown bonds with wedges or hashed bonds. So here we've got a wedge bond here and a hash bond here. It may be drawn to this hash bond here and wedge bond here as well. But to have a chiral center, we must have 4 different substituents around a carbon atom. So let's look at this carbon atom here first. We've got a hydrogen. I'm not numbering these in terms of priority, I'm just numbering how many different substituents there are. Here we've got a chain that goes to an aromatic ring. Here we've got a methyl group, but then that's the same as a methyl group here. So there's only 3 different substituents around that carbon atom there. Okay, so it's not a chiral center. So that's not a chiral center, even though it's drawn in this 3-dimensional manner that shows a wedge and a hashed bond. We can show 3-dimensionality without the molecule having to actually have a chiral center to that position. The other place where we see these wedged and hashed bonds is over here. So now we've got a methyl group, a hydrogen, an aromatic ring, and this carboxylic acid. 4 different substituents. So this is a chiral center. And so therefore we have 1 chiral center in this molecule, and it can be RS. So we've got 2 different stereoisomers. Now, a more precise, more thorough way to do this is we look at every carbon atom in the molecule and look to see if it's got 4 different substituents. But what I've done is I've taken a shortcut and I've ruled out wherever I see a vertex of 2 bonds like this, the remaining 2 bonds must be to hydrogen. So whenever we see a vertex like that with just 2 bonds going from it, we can never have a chiral center because 2 of those substituents are hydrogens. If we see a bond ending like this, that's a methyl group. So that's going to be a CH3, and it's never going to be chiral either because it has 3 identical hydrogens. Similarly, if we see a molecule, a carbon atom within a molecule that has a double bond, that can never be a chiral center because, for one thing, it's flat. We have this sp2 hybridized carbon atom with a p orbital, and so flat carbons like that cannot be chiral. Moreover, when we have a pi bond like that, we've only got 3 substituents around the carbon. We need 4 different substituents to make up a chiral center. So we can say the same thing about this carbonyl carbon here as well. It has a double bond and only 3 substituents around it, so it is also not a chiral center. So there's only 2 stereoisomers of the analgesic ibuprofen. Question 9, ibuprofen again. The stereoisomer that's shown is the more potent one. So when it's sold to you over the counter for your headache or for your sore muscles, it's given to you as a racemic mixture. However, it's known that the stereoisomer drawn here is the more potent of the 2 stereoisomers, or 2 enantiomers. So we're asked, what is the absolute configuration of this molecule? So we've already identified that as the chiral center, and we know that chiral centers can be assigned as either R or S. So you can immediately rule out the E and Z here. That's only for alkenes. So now we're going to assign priority. The easiest one to assign priority to is the hydrogen, and the next one is going to be the methyl group, because when we get to the methyl carbon, the next step along that chain are just 3 hydrogens, whereas when we get to this carbon atom here, or this carbon atom here, both of those go to heavier elements that aren't hydrogen. So I'll just replace these with different colors so they're easier to see. So let's put this one in blue, and let's just expand that carbon there. So that carbon goes to a carbon atom up here, and then another carbon atom down there, and then it's got a pi bond here to a carbon atom. So we make that as a phantom carbon atom. So we expand that pi bond out into a phantom or a dummy atom. Okay, so we've gone one out further along the chain. Let's see whether the other chain is different to that. So this carbon here, we go from that to an oxygen, which is here, and to an oxygen, which is here. And then we've got this pi bond to an oxygen. So we expand that to a phantom or a dummy atom. So we've got 3 things that that carbon atom is linked to. In this priority rules are 3 oxygens versus 3 carbons on the other side. We look for the first point of difference, prioritizing the highest priority through to the lowest priority. This case is very simple because they're all the same atoms. There's no difference in priority. So we've got an oxygen versus a carbon. So this side wins. So this will be the higher priority substituent, and this will be the lower priority. Let's draw that in blue just to be consistent. Okay, now we're lucky, the lowest priority substituent is already away from us here. And so we can just go, and I'll do this in green now, we can go from 1 to 2, from 2 to 3, and from 3 back to 1. We're going in an anti-clockwise direction. So that's a left-hand turn on the steering wheel, or it's the start of the letter S. Okay, so this is the S configuration. So the correct answer is the blue diamond. S is the more potent or more biologically active enantiomer of the non-steroidal anti-inflammatory drug ibuprofen. Okay, last question. Question 10. Racemic ibuprofen that we were just talking about can be treated with this chiral amine, one enantiomer of this chiral amine called phenylethylamine. And we're treating with the S enantiomer of phenylethylamine. How many diastereomeric salts can form? So let's not draw the whole of ibuprofen, but let's just say that we have R ibuprofen is some molecule with a carboxylic acid, and S ibuprofen is some chiral molecule with a carboxylic acid like that. Just tidy this up. When you react those with the S amine, we're not drawing the whole structure, we're just drawing it diagrammatically like this. Each of those enantiomers of ibuprofen can form a salt with the one enantiomer of the amine. So we can get the R carboxylate ion paired with the S ammonium salt, or ammonium ion. So there's our ions there. And we can have the, oops, the S-ibuprofen carboxylate, because it's now donated its proton to the basic amine of phenylethylamine. There it is there. But we've only got one enantiomer, so in either case it's the S enantiomer of the ammonium ion that is ion paired with the carboxylate of ibuprofen. So there's two different salts that can form, and these are diastereomers. So if they were covalently linked, then we would have a compound with two chiral centers, and they could be either R-ibuprofen S-amine or S-ibuprofen S-amine. Same with a salt. Even though it's not a covalent bond, we can still have those ions ion pairing with each other. And so overall, the salts are also diastereomeric. So these are diastereomeric salts. And so therefore, there's two different possibilities. And indeed, this is a way that you can actually resolve racemic ibuprofen. You treat it with a chiral amine, like phenylethylamine, of which you've only got one enantiomer, and then there's two possible salts. And because they're diastereomers of each other, they'll have different properties. For example, they'll have different solubilities in solvents. And indeed, this is an undergraduate experiment where when you form these two salts, one is less soluble in water, and so it will crash out of aqueous solution. You can filter it off, and then you can do acid-base chemistry to retrieve the ibuprofen from the salt mixture. Okay, so that's the end of that Kahoot quiz. Hopefully you found that useful in revising some concepts around stereochemistry and chirality, and thanks for watching.